The thermometer outside read 47 degrees below zero. Inside James McKinnon's cabin, deep in the Yukon territory in January of 1896, the reading should have been perhaps 0 to 5 degrees above, maybe 10 if a man was lucky and burning wood constantly. That's what every other cabin in the region was experiencing. Men huddled close to red-hot stoves, wearing every piece of clothing they owned, watching their breath freeze in the air inside their own shelters. Water froze in buckets 3 feet from the fire. Ice formed on the inside of cabin walls. Survival was a full-time occupation that required burning massive amounts of wood and still accepting brutal discomfort. But inside James McKinnon's cabin, the thermometer read 18 degrees below zero. Still cold by any reasonable standard, certainly well below freezing, but 29 degrees warmer than outside. 29 degrees warmer in a cabin that wasn't burning any more wood than his neighbors' cabins. 29 degrees warmer in a structure that looked, from the outside, like it had been abandoned and buried by winter, because it had been buried, deliberately, intentionally. James McKinnon had spent 3 days in early December shoveling snow onto his cabin roof, piling it against his walls, burying his structure under 6 to 8 feet of compacted snow until only his chimney and a carefully constructed entrance tunnel remained visible. His neighbors thought he'd lost his mind. They said he was trying to kill himself, that burying a cabin was the act of a man who'd gone mad from isolation and cold. They predicted he'd suffocate from lack of air, or that the weight of the snow would collapse his roof, or that he'd be trapped and unable to escape if fire broke out. They said many things, all of them variations on the theme that James McKinnon was a fool who would die for his foolishness. But January had come, bringing cold that tested every structure and every survival strategy, and James was not only alive, but warmer than anyone else within 100 miles. When a mail carrier named William Trask struggled through the deep snow to deliver mail to the scattered cabins along his route, he couldn't find James's cabin. He knew roughly where it should be, but all he saw was a mound of snow with smoke rising from what looked like a small hole. Assuming James had either abandoned his cabin or died, Trask was about to move on when he heard a voice. "Trask, down here!" Trask looked down and saw a tunnel entrance barely 3 feet high with wooden framing holding it open. James McKinnon's head appeared in the opening. "Come down, get warm, you look half frozen." Trask, confused and concerned, crawled down into the tunnel. It descended at a slight angle for about 12 feet, then opened into a small vestibule. From there, a door led into the cabin proper. When Trask stepped through that door, he stopped in shock. The cabin was dim, lit only by a single lamp and the glow from the stove, but it was noticeably warmer than any cabin Trask had visited on his route. Not warm by southern standards, but dramatically warmer than the 0 to 5 degree interiors he'd been enduring all week. "How?" Trask asked, looking around the cabin that appeared to be functioning normally despite being buried under tons of snow. "How is it this warm? And how are you getting air? And how is your roof not collapsed?" James gestured toward the ceiling, which showed no signs of stress or sagging despite the enormous load above it. Snow is insulation. The best insulation that exists. I'm not fighting winter anymore. I'm using it. Every foot of snow on my cabin is a foot of insulation between me and the cold. My neighbors are trying to keep winter out with thin walls. I buried my cabin in winter, and winter is keeping me warm. What James McKinnon had done was something his neighbors considered insane, but what Arctic peoples had known for thousands of years. Snow, properly used, is not the enemy of warmth. It's one of the greatest insulators nature provides. By deliberately burying his cabin under massive amounts of snow, James had created a structure with insulation values far exceeding anything possible with wood, moss, or any conventional building material available on the frontier. His 29-degree temperature advantage was not luck or magic. It was physics, applied with knowledge borrowed from Inuit snowhouse construction and adapted to a log cabin context. And the story of how he learned this, why he implemented it, and why everyone was convinced it would fail reveals deep truths about insulation, thermal mass, and the counterintuitive principle that sometimes the best way to stay warm is to embrace the cold. James McKinnon was born in Ontario in 1862, but he'd spent most of his adult life in the far north. He'd worked as a guide and translator for various expeditions into the Arctic, and during those years, he'd lived with Inuit communities, learning their language and their survival techniques. One thing that fascinated James was the snow house, what most people called an igloo. The Inuit could build a snow house in a few hours using nothing but packed snow blocks cut from a drift. These structures, made entirely from frozen water, provided shelter warm enough that the interior could reach 40 to 50 degrees Fahrenheit, even when outside temperatures were 40 or 50 below. The heat source was just body heat and perhaps a small seal oil lamp. No massive fire, no constant wood feeding, just the remarkable insulating properties of snow, keeping occupants comfortable. James had spent nights in snow houses and experienced this phenomenon firsthand. The physics made sense once explained. Snow, especially wind-packed or compressed snow, is approximately 90 to 95% trapped air. Air is an excellent insulator when it's not moving. The ice crystals in snow create a matrix that holds air in countless tiny pockets. Each pocket is isolated, preventing convection. Heat can only escape through the slow process of conduction through the ice crystals. And ice, while better conductor than air, is still a relatively poor conductor compared to most building materials. The R value of snow, a measure of thermal resistance, ranges from approximately 3.5 to 5.0 per inch, depending on density and structure. For comparison, wood has an R value of approximately 1 per inch. Moss or grass insulation might achieve R2 to R3 per inch. A foot of compacted snow provides R value of 40 to 60. That's insulation performance far exceeding any wall construction possible with frontier materials. James had learned this not from books or formal education, but from experiencing it, from watching Inuit elders build snow houses that kept children warm in temperatures that would kill unprotected humans in minutes, from understanding through direct observation that snow was not just a burden to be endured, but a resource to be used. When James established his own cabin in the Yukon in 1894, he knew winters would be brutal. Temperatures routinely dropped to 40 or 50 below. Firewood, while available, required enormous effort to cut and haul. He'd seen other trappers and miners work themselves to exhaustion cutting wood, burning it constantly, and still barely maintaining livable conditions. James decided he would build differently. He would build a cabin that could be buried under snow, turning winter itself into his primary insulation system. The first challenge was structural. A standard log cabin roof couldn't support 6 to 8 feet of snow. The load would be enormous, potentially 20 to 30 tons depending on cabin size and snow density. James needed to build a roof strong enough to handle that load without collapsing. He spent the summer of 1894 cutting and preparing massive logs. His roof beams were logs 12 to 14 inches in diameter, far larger than typical cabin rafters. He spaced them 12 inches apart, center to center, creating a roof structure with enormous redundancy. Each beam could individually support several tons. Together, they could handle the snow load he intended to place on them. The roof pitch was moderate, about 35 degrees, steep enough to shed loose snow, but not so steep that compacted snow would slide off. James wanted the snow to stay on the roof. That was the whole point. Over the structural beams, he laid a deck of split logs, flat side up, fitted tightly together. Over this deck, he placed a layer of birch bark for waterproofing. Over the bark, he spread 6 inches of sawdust mixed with dry moss. This layer would provide initial insulation before the snow arrived and would also help distribute the snow load evenly across the deck. The result was a roof that weighed perhaps 2 tons empty, but could support 30 tons loaded. James had built in a safety factor of 15 to 1, far exceeding what any conventional cabin provided. The walls were equally overbuilt. James used vertical post construction with massive corner posts, 12 inches square, set 4 feet into the ground. Between these posts, he stacked horizontal logs, each one carefully fitted and chinked with moss and clay. But he built the walls double thickness. The outer wall was 8-inch logs, then a 6-inch gap filled with sawdust and moss, then an inner wall of 6-inch logs. This double wall construction provided significant insulation even before snow was added. The total wall thickness was approximately 20 inches. Most cabins had 8 to 12-inch single wall thickness. James had nearly doubled the wall mass and incorporated an insulation cavity. The foundation was critical. James dug down 4 feet below the permafrost layer in this region and laid a foundation of flat stones. The floor joists rested on this foundation, elevated above ground level. The floor itself was double-layer split logs with sawdust between the layers. This created an insulated floor that prevented heat loss downward into the frozen ground. Every element of the cabin was designed to retain heat and to support enormous weight. By September 1894, the cabin was complete. It looked strange to visitors. The walls were too thick. The roof was overbuilt. The whole structure seemed like massive overkill for a single man's trapping cabin. A miner named Tom Davidson examined the construction and asked the obvious question: why build so heavy? You planning to put a second story on this thing? James smiled. I am planning to put a second story on it. A story made of snow, 10 feet of snow. That's the insulation system, Davidson laughed. You're going to bury your cabin in snow? On purpose? That's the craziest thing I've heard. Snow is what we're trying to keep off our roofs. You want to pile it on? James tried to explain the insulation principle, but Davidson and others couldn't get past the idea that deliberately burying your cabin was suicidal. They left, shaking their heads, convinced James would learn the hard way that his plan was flawed. The first winter, 1894 to 1895, was moderate by Yukon standards. James let natural snowfall accumulate on his roof, and by midwinter he had approximately 3 feet of snow on the structure. He noticed immediately that his cabin was warmer than it should be. With minimal fire, he maintained interior temperatures around 20 degrees, compared to the 0 to 5 degrees his neighbors were achieving. The difference was noticeable but not dramatic enough to convince skeptics. They attributed it to his thick walls and good construction, not to the snow on the roof. But James knew the 3 feet of snow was helping. It was providing R value of approximately 15 to 20, adding to the R value of his roof deck and sawdust layer. He estimated his roof had total R value around 40 with the snow layer included. That was excellent insulation by any standard, but James knew it could be better. That summer, he prepared for a more aggressive approach. He built a snow shovel with a wide blade, designed for moving large volumes of compacted snow. He constructed wooden forms that could be used to shape snow into stable walls around his cabin. He planned the entrance tunnel, calculating the angle and depth needed to create an airlock that would prevent cold air from flowing directly into the cabin, and he waited for winter. Winter 1895 to 1896 arrived in November. By early December, snowfall had provided about 2 feet of accumulation. James began his project. He started by shoveling snow from the surrounding ground onto his roof. He worked methodically, lifting shovelfuls of snow and tossing them onto the roof. The snow packed down under its own weight. He continued until he had approximately 6 feet of snow on the roof, compacted to perhaps 4 feet of dense pack. Then he began building snow walls around the cabin. Using his wooden forms, he shaped the snow into walls that extended from the ground up to roof level. These walls were approximately 3 feet thick. He packed them carefully, ensuring good compaction, creating solid barriers that would provide insulation and wind protection. Around the entire perimeter of the cabin, he built these snow walls, burying the log walls underneath. By the time he finished, the cabin looked like a mound, a hill of snow with only the chimney protruding from the top. The entrance required special attention. James dug a tunnel starting about 20 feet from the cabin wall, descending at a 15-degree angle. The tunnel went down about 4 feet, then turned and ran horizontally to an entrance door on the cabin's south wall. This created an airlock. Cold air, being denser than warm air, would sink and pool in the tunnel. Warm air from the cabin would stay inside. The vertical drop ensured that the cabin interior was always above the level where cold air could accumulate. He lined the tunnel with boards to prevent collapse and to provide a stable walking surface. At the outer tunnel entrance, he built a snow vestibule, a small chamber where he could shake off snow and adjust to the temperature transition before entering the tunnel proper. The entire entrance system was about 25 feet long from outside to cabin interior. By mid-December, the project was complete. James's cabin was fully buried under 6 feet of roof snow and 3 feet of wall snow. The total additional weight on the structure was approximately 25 to 30 tons. The massive roof beams handled the load without stress. Inside, James began monitoring temperatures carefully. With a small fire in his stove, burning perhaps 2 pounds of wood per hour, the interior temperature stabilized at around 10 to 15 degrees Fahrenheit when outside. Temperature was 30 below, a 20 to 25 degree difference with minimal heat input. As January 1896 arrived and temperatures dropped to their seasonal lows, the advantage became even more dramatic. On January 12th, 1896, the temperature outside reached 47 below zero. James's cabin interior, with his small fire burning at the usual rate, held at 18 below, 29 degrees warmer. The neighbors who'd survived similar cold by burning wood at 4 to 6 pounds per hour and achieving 0 to 5 degree interiors were using 3 times as much fuel and achieving temperatures 30 to 40 degrees colder than James's cabin. When William Trask discovered James's buried cabin and experienced the relatively warmth inside, he was astounded and confused in equal measure. How could burying a structure make it warmer? It defied intuition. James explained patiently, using concepts he'd learned from the Inuit and verified through his own measurements. Snow is insulation. My roof probably has R value around 100 now with all the snow on it. My walls have R value around 70 or 80. That means heat escapes very, very slowly. The small fire I'm burning produces enough heat to replace what's lost. Temperature stabilizes at whatever point heat input equals heat loss. With such good insulation, that point is much warmer than my neighbors' cabins with poor insulation. Trask listened, tried to understand, and finally asked, "But how do you get air?" "You're buried. You must be breathing stale air, maybe poisoning yourself with smoke." James pointed to 2 small pipes protruding through the ceiling, ventilation pipes. One pulls fresh air in, one lets stale air out. The pressure difference is small, but it's enough to provide continuous air exchange. I'm breathing outside air, warmed slightly as it comes through the pipe that runs through the insulated roof space. No smoke, no suffocation, just fresh air. Trask examined the system, still amazed. "And you're not worried about being trapped? If there's a fire or an emergency, how do you get out?" James gestured toward a secondary exit, a wooden hatch in the floor that led to a small tunnel extending north about 15 feet before surfacing. "Emergency exit. If the main tunnel's blocked, I can get out through here. Takes about 2 minutes to dig through the last foot of snow if it's gotten covered. I'm not trapped. I'm protected." Trask left James' cabin and continued his mail route, telling everyone he met about the buried cabin that was warmer than any standing cabin. The story spread quickly. Some dismissed it as exaggeration. Others were intrigued enough to visit James and see for themselves. By late January, James had hosted a dozen visitors, all coming to verify the temperature claims and understand the system. A trapper named Samuel Porter visited on a day when outside temperature was 38 below. He measured the interior himself using his own thermometer, 14 below inside, 24 degrees warmer than outside. He felt the walls, which were noticeably cool but not frozen. He examined the structure, looking for signs of stress or damage from the snow load. Everything was solid. "This works," Porter said, a note of wonder in his voice. "This actually works. You've built a cabin that uses winter to keep you warm. That's—" He searched for the right word. "That's brilliant. Why isn't everyone doing this?" James shrugged. "Because it looks crazy. Because it's not how cabins are supposed to be built. Because it requires understanding that snow is a resource, not just a burden. Most people can't see past the strangeness to understand the principle." Porter nodded slowly. "Will you teach me? Next summer, will you help me build a cabin like this?" James agreed. That summer of 1896, James helped 3 different trappers build cabins designed to be buried in snow. Each cabin was customized to the builder's specific needs, but all incorporated the key elements: massive structural capacity to handle snow load, double wall construction for base insulation, carefully designed entrance tunnels with airlock effect, ventilation systems that provided fresh air without losing heat. By the winter of 1896 to 1897, 4 buried cabins existed in the region, all showing similar performance improvements over conventional structures. If you're fascinated by these forgotten survival techniques that could still be useful today, please take a moment to subscribe to this channel. Hit that subscribe button and turn on notifications. We explore historical innovations that solved real problems with elegant simplicity, knowledge that's been lost but shouldn't be. Your subscription helps us continue this work. Now let's dive into the science of why burying a cabin in snow worked so spectacularly well. The physics of snow insulation operates on principles that modern building science fully understands, but that frontier builders rarely considered. First, the thermal conductivity of snow. Snow is a composite material consisting of ice crystals and trapped air. The thermal conductivity of ice is approximately 2.2 watts per meter per Kelvin. The thermal conductivity of air is approximately 0.025 watts per meter per Kelvin. Snow, being mostly air, has thermal conductivity much closer to air than to solid ice. The exact value depends on snow density. Fresh, fluffy snow might be 95% air, with conductivity around 0.05 to 0.1. Settled snow might be 80 to 90% air, with conductivity around 0.1 to 0.3. Heavily compacted snow, what James was using, might be 70 to 80% air, with conductivity around 0.3 to 0.5. For comparison, wood has thermal conductivity around 0.12 to 0.20, so even compacted, snow is only about 2 to 3 times more conductive than wood. But James was using 6 feet of snow on his roof and 3 feet on his walls. Even if the thermal conductivity is slightly higher per inch than wood, the total thickness more than compensated. Total thermal resistance equals thickness divided by thermal conductivity. James's roof with 6 feet, 72 inches, of snow at conductivity, 0.4 had total R value around 180, divided by 0.4 equals approximately 150. His walls with 3 feet, 36 inches, had R value around 90. These are insulation values far exceeding anything possible with frontier materials. Second, the principle of trapped air preventing convection. In materials like fiberglass insulation or snow, the insulating power comes not from the solid material, but from the trapped air. Air itself is an excellent insulator, but only when it's not moving. Moving air carries heat through convection, which is far faster than conduction. Snow traps air in millions of tiny pockets separated by ice crystal walls. Each pocket is isolated. Air can't move from one pocket to another. This eliminates convection within the insulation layer. Heat can only move by conducting through the ice crystals from one air pocket to the next. This slow, step-by-step process dramatically reduces heat transfer rate. Third, The effect of thickness on heat loss. Heat flow equals thermal conductivity times area times temperature difference divided by thickness. Doubling the insulation thickness halves the heat flow rate. James's 6-foot thick roof insulation compared to a conventional roof with perhaps 8 inches of wood and 6 inches of sawdust, total 14 inches, had approximately 5 times the thickness. Even accounting for slightly higher thermal conductivity of snow versus sawdust, the heat loss rate through James's roof was approximately 1/3 to 1/5 the heat loss rate through conventional roofs. Similar logic applied to his walls. Fourth, the elimination of air infiltration. One of the biggest heat losses in frontier cabins was air infiltration. Cold air leaking in through gaps around doors and windows, through chinking cracks, through every imperfection in the structure. This infiltration brought cold air in and let warm air escape, creating heat loss far exceeding conduction losses through solid walls. James's buried cabin had almost zero infiltration. The entrance tunnel acted as a perfect airlock. Cold air sank into the tunnel and stayed there. Warm air from the cabin interior couldn't rise out through the tunnel because it had to go down first, against its natural buoyancy. The cabin was essentially sealed, with controlled ventilation through the pipes rather than uncontrolled infiltration through cracks. Fifth, the thermal mass effect. The snow surrounding James's cabin, weighing 25 to 30 tons, had significant heat capacity. If the cabin interior warmed above the snow temperature, the snow would absorb excess heat. If the interior cooled below the snow temperature, the snow would release heat. This thermal mass created temperature stability, damping fluctuations. The inside temperature couldn't change rapidly because any change required heating or cooling the adjacent snow mass. Modern analysis of James's system yields quantitative results. His cabin was approximately 12 feet by 16 feet. Interior dimensions 192 square feet of floor area. With 8-foot walls and peaked roof, total interior volume was approximately 2,000 cubic feet. The surface area of walls and roof was approximately 600 square feet. With average R value around 100, the total heat loss coefficient equals area divided by R value equals 600 divided by 100 equals 6 BTUs per hour per degree Fahrenheit difference. When outside temperature was 47 below, minus 47 degrees, and inside was 18 below, minus 18 degrees, the temperature difference was 29 degrees Fahrenheit. Heat loss equals coefficient times. Temperature difference equals 6 times 29 equals 174 BTUs per hour. James's small fire, burning 2 pounds of wood per hour, produced approximately 16,000 BTUs per hour gross energy. With stove efficiency around 50% for a well-designed stove, useful heat output was approximately 8,000 BTUs per hour. But most of this went to heating fresh ventilation air, not to replacing envelope losses. The ventilation airflow was approximately 10 cubic feet per minute, or 600 cubic feet per hour. Heating this air from minus 47 to minus 18 required approximately 600 times specific heat of air times 29 degrees equals approximately 6,000 BTUs per hour. Adding the envelope loss of 174 BTUs per hour gives total heat requirement approximately 6,200 BTUs per hour. James's stove provided 8,000, leaving margin for thermal mass heating and system inefficiencies. The calculation shows the system was balanced. Small heat input, around 2 pounds of wood per hour, was sufficient to maintain minus 18 degrees interior temperature because heat losses were so low. For comparison, a conventional cabin with R value around 15 on walls and 20 on roof, averaging perhaps 17, would have heat loss coefficient around 600 divided by 17 equals 35 BTUs per hour per degree. At the same temperature difference, -47 outside and -18 inside would require heat input. Around 35 times 29 equals approximately 1,000 BTUs per hour just for envelope losses. But conventional cabins couldn't achieve -18 inside. They'd be 0 to 5 degrees, approximately a -15 to -25 Fahrenheit. At -20 average, interior with -47 outside, the difference is 27 degrees. Heat loss is 35 times 27 equals approximately 950 BTUs per hour for envelope. Ventilation heating for 600 cubic feet per hour from -47 to -20 requires approximately 600 times 0.018 times 27 equals approximately 290 BTUs per hour. Total heat requirement approximately 1,240 BTUs per hour. But typical fires burning 6 pounds per hour produced approximately 48,000 BTUs per hour gross, or 24,000 useful at 50% efficiency. Why was so much more fuel needed if the heat requirement was only 1,240 BTUs per hour? Because actual cabin R values were much lower than 15 to 20. Air infiltration, thermal bridging, and poor construction reduced effective R value to perhaps 5 to 8. This increased heat loss dramatically, requiring the massive fire inputs that frontier trappers actually experienced. James's cabin, with minimal infiltration and high R values, achieved the theoretical efficiency that conventional cabins couldn't approach. The practical operation of James's buried cabin required specific techniques. Ventilation was critical. Without fresh air, carbon dioxide and moisture would accumulate to dangerous levels. James's 2 ventilation pipes, each about 3 inches in diameter, provided approximately 10 cubic feet per minute of fresh air through natural convection. Warm, moist air rose and exited through one pipe. Cold, dry air entered through the other pipe, was warmed slightly by contact with the pipe walls as it descended, and entered the cabin. This natural convection system required no pumps or fans, just careful design of pipe lengths and positions to ensure adequate pressure difference. Snow maintenance was another consideration. Fresh snowfall would occasionally cover the chimney top or ventilation pipes. James had to clear these regularly to ensure proper exhaust and ventilation. He'd installed tall pipes specifically to reduce the frequency of this maintenance. In typical winters, he'd clear snow off the pipes 2 to 3 times per month. Emergency egress required thought. James's floor hatch and tunnel provided an alternate exit that could be cleared quickly if needed. He kept a shovel inside the cabin specifically for this purpose. In practice, he never needed to use the emergency exit, but having it provided psychological comfort and actual safety backup. Structural monitoring was important. James inspected his roof beams monthly during the first winter, looking for any signs of stress, cracking, or sagging. He found none. The beams were operating well within their capacity. After the first winter proved the structure was sound, he reduced inspections to once per season. The entrance tunnel required occasional maintenance. The packed snow walls would settle slightly over time. James would recompact them or add fresh snow as needed to maintain stable tunnel geometry. The wooden framing prevented complete collapse even if the snow around it deteriorated. The spread of the buried cabin technique through the Yukon and Alaska regions was limited by several factors. First, it required substantial structural investment. The massive roof beams and doubled walls required perhaps 50% more timber than conventional construction. In areas where timber was scarce, this was prohibitive. Second, it required specific snow conditions. The technique worked best in regions with consistent, deep snow cover from early winter through late spring. In areas with variable snow or frequent melting and refreezing, the insulation value was less predictable. Third, it required tolerance for unconventional living. Many people found the idea of living in a buried structure claustrophobic or disturbing. The low ceiling of the entrance tunnel, the lack of windows, the constant awareness of being underground, these factors created psychological resistance that not everyone could overcome. Fourth, it required understanding principles that most frontier builders didn't possess. The concept of using snow as insulation was counterintuitive enough that explaining it to skeptics was difficult. Many people simply couldn't accept that burying your cabin could make it warmer. Despite these limitations, approximately 30 buried cabins were built in Alaska and the Yukon between 1896 and 1910, all based on James's design or variations thereof. Each one showed similar performance improvements: warmer interiors with less fuel consumption. The occupants universally reported satisfaction with the comfort and efficiency. But the technique remained niche, known only to a small community of trappers and miners who were willing to try unconventional approaches. James McKinnon continued living in his buried cabin until 1904, when he returned to Ontario to care for aging parents. His cabin was taken over by another trapper who operated it successfully for another decade. The structure remained standing and functional until the 1920s. When it was finally abandoned and left to collapse naturally. By that time, more than 30 winters had tested the design, and it had never failed. The buried cabin concept was largely forgotten by the mid-20th century, as the frontier era ended and modern heating systems became available. But indigenous peoples, particularly the Inuit, never forgot. They continued building snow houses when needed, using the same principles James had adapted to his log cabin. In the late 20th century, architects and engineers began rediscovering earth-sheltered and snow-covered building designs. Modern earth-sheltered homes, built partially or fully underground with soil covering the roof, operate on the same principles James demonstrated. The earth provides insulation and thermal mass, dramatically reducing heating and cooling loads. Some experimental cold climate buildings use seasonal snow accumulation as part of their insulation strategy, essentially a modern version of James's approach. The science validates what James knew from experience. Snow is excellent insulation when properly used. Modern measurements of snow, R values, confirm the estimates James would have made based on performance. Buildings covered with several feet of snow show dramatic reductions in heat loss. The principle is sound, proven both historically and scientifically. The practical lessons from James's buried cabin apply to modern cold climate building. First, insulation thickness matters more than most people realize. Doubling insulation more than doubles efficiency because it also reduces thermal bridging and infiltration. Very thick insulation, whether conventional materials or unconventional like snow, creates dramatic performance improvements. Second, air sealing is as important as insulation. James's tunnel airlock eliminated infiltration. Modern building science emphasizes continuous air barriers for the same reason. Uncontrolled air movement wastes enormous amounts of energy. Third, natural materials can provide excellent insulation if used in sufficient quantity. Snow, earth, straw bales, sawdust. These materials are inexpensive or free, but require greater thickness than manufactured insulation. The trade-off of labor and space for material cost makes sense in many contexts. Fourth, counterintuitive solutions often work better than conventional approaches. Burying a cabin to keep it warm seems backwards until you understand the physics. Many modern energy efficiency strategies seem counterintuitive but are actually optimal. We need to be willing to question assumptions. Fifth, learning from indigenous knowledge can provide solutions to problems that seem new but are actually ancient. The Inuit perfected snow house construction over thousands of years. James adapted their knowledge to a different context. Modern builders can benefit from studying traditional techniques from any climate or culture. The barrier to adopting snow-covered building designs today is primarily psychological and regulatory. Building codes don't know how to handle structures designed to be buried in snow. Insurance companies are uncomfortable with unconventional designs. Architects and builders lack experience with these systems. These are all surmountable barriers, but they require effort to overcome. For people building in remote, cold locations where conventional building is difficult and expensive, James's approach might still be optimal. A well-designed, super-insulated structure that uses seasonal snow as additional insulation could dramatically reduce heating costs and improve comfort. The technology is simple. The principles are proven. The question is whether anyone is willing to apply them. Before we conclude, I want to ask one more time. If this story opened your mind to new ways of thinking about building and insulation, please subscribe to this channel, hit that subscribe button, turn on notifications, and join our community learning from historical innovations. Your support makes this work possible. Thank you. James McKinnon's 29-degree temperature advantage came from understanding a simple principle that most people missed. Snow is not just cold, it's cold insulation. Those are different things. Fighting snow, keeping it off your roof, preventing accumulation, these strategies treat snow as the enemy. James treated snow as a resource. He deliberately buried his cabin in the very thing others were desperately trying to avoid. The result was the warmest cabin in the Yukon, heated with the least amount of wood. His neighbors, using 3 times more fuel and working 3 times harder, achieved interiors 30 degrees colder. The efficiency advantage was overwhelming. The comfort advantage was life-changing. Yet most people couldn't or wouldn't adopt his approach because it looked wrong. A cabin should stand above ground, visible and accessible. A cabin buried in snow looked like defeat, like giving up, like surrender to winter. But James understood that surrender to winter was actually victory over cold. By accepting snow, by welcoming it, by building it into his insulation system, he turned winter from enemy to ally. This is the deep lesson. Sometimes the thing you're fighting is the thing you should be using. Sometimes resistance is less effective than acceptance. Sometimes the solution involves embracing what seems like the problem. Thank you for watching this story about James McKinnon and his buried cabin. If this changed how you think about cold, insulation, or unconventional solutions, please share it with someone who might benefit. And remember that sometimes the best way to fight the cold is to stop fighting the cold. Sometimes burial is protection. Sometimes winter can be a blanket instead of a blade. James McKinnon knew this. His 29-degree advantage proved it. The cabin everyone thought would be his tomb became the warmest home in the Yukon. Sometimes what looks like madness is actually genius. Sometimes the fool is the only wise man, and sometimes the best way to survive winter is to let winter bury you alive.